Okay, welcome to the deep dive. Today we are taking a stack of our source material, specifically a fantastic talk given at Ruby Kaigi by Maxime Chevalier-Boisvert, and we're doing a deep dive into the really exciting evolution of Ruby's performance story. We're tracing the journey from YJIT, which has made such a huge impact,
It really has.
towards a brand new project on the horizon called Zjit.
That's right. Our mission for this deep dive is to really unpack this technical presentation from the YJIT team.
Okay.
We want to understand the key challenges they faced, the innovations they're now exploring with Zjit, and, well, why all these efforts aren't just interesting technical puzzles,
Right.
but are truly crucial for the language's long-term future.
So getting a handle on what's next for Ruby speed.
Exactly. Think of this as getting your head around what's next in making Ruby seriously fast.
So let's unpack this by starting where this modern JIT story for Ruby really kicked into high gear, YJIT.
Okay?
I remember hearing about this project starting back in 2020, and honestly, it felt a little bit like a moonshot at the time.
Yeah, it kind of did.
It began as just a prototype. They even nicknamed it Microjet over at Shopify.
Yeah, and they had a pretty tight timeline for that initial prototype, just 3 months.
Wow, 3 months.
I know. They managed to get some speed-ups on certain smaller benchmarks, maybe up to 10%.
Wow.
But on their real bench, which is supposed to represent more typical workloads, it actually underperformed at first.
Oh, really? Why was that?
Well, they spent too much time constantly jumping back and forth between the JIT compiled code and the interpreter. Too much overhead there initially.
Okay. But hey, that early promise was enough to get the big green light for a real JIT project.
Right. A proper one.
This time, the goal was 9 months, and they had specific targets. Clear double-digit speedups on OptCarrot,
The classic Ruby benchmark, yeah.
single-digit gains on Railsbench, and importantly, a really low warm-up time.
Critical. You didn't want to wait 5 minutes for your app to get fast after starting it.
Exactly.
And this is where it gets really interesting. They didn't just meet those goals, they blew past them.
Oh, nice.
YJIT ended up working better than they initially even dared to hope. They saw clear double-digit speedups on realistic benchmarks, sometimes upwards of 20%.
20%, wow.
And the absolute game changer was that they could run Shopify's actual storefront rendering infrastructure on it,
The real deal.
serving real web requests from day one. That proved it worked in the messy real world.
That's huge validation.
Totally.
And that kind of success naturally led to it being presented at Ruby Kaigi Takeout in 2021.
Made sense? Show the results.
Showing those numbers publicly clearly caught attention. Takashi Kokubun from the Ruby core team extended an invitation for it to be upstreamed into C Ruby.
Which was a significant step and very well received, including by Mats, Ruby's creator.
It's great buy-in.
It was merged shortly after and became a standard part of Ruby 3.1.
And it hasn't just stayed still, right? It's improved since then.
Oh yeah, it's gotten better.
Yeah.
Performance has improved significantly over the years, particularly on OptCarrot, which, as you said, is really seen as the most important Ruby benchmark for JITs. Right. With Ruby 3.3, YJIT hit a massive milestone, a 3x speedup over the Ruby 2.7 interpreter baseline on OptCarrot.
3 times faster, just by upgrading Ruby versions and enabling YJIT.
Yep. Pretty incredible.
That is incredible. And it's worth emphasizing, as the talk did, that YJIT's success isn't just down to 1 or 2 people.
No, absolutely not.
It's been a huge team effort with many contributors over the years.
Including some amazing work from Takashi Kokubun after it was upstreamed. He really pushed it forward, too.
Good point.
Absolutely. And we've seen this translate into widespread real-world deployment. It's not just Shopify,
Right.
where they're now seeing closer to 20% end-to-end speed-ups on their storefront requests, thanks to YJIT.
Still significant gains.
Definitely. But it's also deployed at Mastodon, Discords, and dozens of other tech companies. People are reporting excellent results, often hitting 30% speedups just by enabling it.
That anecdotal evidence is so powerful. I loved the story shared in the talk about someone from Zendesk.
Oh yeah, that was a good one.
They updated to Ruby 3.3.1 and literally just enabled YJIT with the flag
Flip the switch.
and saw an immediate 20% performance improvement, just like that.
That kind of result, flipping a switch for a huge speedup, gets people talking.
Totally.
And, more importantly, gets people upgrading.
It really does. And that ties directly into a crucial point. Performance is a feature.
It absolutely is. If you can tell people the latest Ruby is 15% faster, they're eager to upgrade.
You don't have to sell them on abstract concepts. The value is immediate and tangible.
Exactly. We're seeing this motivate more and more adoption of the latest Ruby versions.
And you can see this progress for yourself. The site speed.yjit.org tracks these benchmarks.
It's public.
For example, on the liquid render benchmark, you'll see around a 2.8x speedup with YJIT 3.4 compared to the interpreter.
Pretty solid.
Across a representative set of benchmarks, the average is currently sitting around 2x faster. YJIT genuinely changed the game for Ruby performance.
Which is fantastic. We achieved significant real-world speedups, a huge success story.
Okay, but. There's always a but in any engineering journey, isn't there?
Yeah, exactly. The talk title itself gives a hint, and the presentation made it clear. They're starting to hit something of a performance plateau with YJIT.
Plateauing, okay.
While the initial versions delivered massive gains, the difference between more recent versions, like YJIT 3.3 and the development version of 3.4, shows smaller cumulative gains, maybe only around 6–8% total. And it's not consistent across all workloads.
All right, not everywhere.
They even mentioned one report showing basically the same performance between 3.3 and 3.4 in some cases.
Okay, that makes sense, right? Every architecture has limits.
Sure.
And things like database calls or external API requests are always going to be bottlenecks that a JIT can't magically fix.
True, but there's also the issue with YJIT's performance on certain micro-benchmarks.
Ah, okay.
The talk brought up one that circulated recently involving a massive number of nested loop iterations accessing array.
Oh yeah, that one. It looked almost unrealistically simple. Just a few lines of code with intense loops. Like, who writes code like that?
It does look deceptively simple. But on that specific benchmark, even with YJIT enabled, Ruby was only performing about the same speed as PHP.
Okay, PHP speed, fine.
Which is fine, but it was orders of magnitude slower than JavaScript JITs executing the identical trivial loop code.
Orders of magnitude? Ouch! Okay, wait. Why does that specific, seemingly synthetic micro-benchmark matter so much?
Right, good question.
You'd think code like that doesn't really reflect a complex, real-world Rails application, for instance.
What's fascinating here is what that micro-benchmark exposes.
Okay.
If Ruby performs poorly on something so basic and fundamental, executing tight loops with simple operations, it strongly suggests there are fundamental inefficiencies at that very low level of code execution.
Ah, I see.
And since real-world applications, even complex ones, are ultimately built upon these basic operations, fixing those core inefficiencies should translate into performance improvements in real applications, even if it's not a direct 1.1 mapping from the micro-benchmark score.
So it reveals a weakness.
It's about addressing the root cause. The feeling is, we know we can do better at this fundamental level.
So it's less about winning that one specific benchmark game and more about identifying and fixing underlying weaknesses that the benchmark makes visible.
Precisely. And this relentless drive for performance isn't just academic or about benchmark bragging rights. Performance is a feature, as we discussed.
Drives upgrades, adoption.
Exactly. But if we connect this to the bigger picture that the talk emphasized, it's also absolutely crucial for Ruby's long-term health and survival.
How so?
Well, in a world where computing demands are constantly increasing, optimizations are relentless, and single-core CPU performance is starting to plateau.
Right, Moore's law slowing down for single cores.
A language has to be fast. If Ruby becomes a significant bottleneck, that's a serious problem for its relevance. The ultimate goal here is a truly world-class Ruby JIT, one that can compete with the best out there.
Okay, the stage is set beautifully. YJIT has been a massive success story, demonstrating the potential.
Huge success.
But it's starting to hit limits, and the need for performance is more critical than ever. So here comes the next act. Zjit.
Yes, introducing Zjit, Z-J-I-T.
Got it.
This is a project the YJIT team quietly started about 2.5 months before this Ruby Kagi talk.
Pretty recent then.
Very recent. And it's explicitly presented not just as YJIT 2.0, but as a prototype of a completely next-generation Ruby JIT compiler.
A fresh start, but building on experience.
Exactly. They're not throwing away all that hard work, right? It's built directly on everything learned from the past 4.5 years of intense YJIT development.
Yeah.
Hundreds of experiments run, and mountains of production data from Shopify and other users.
Okay, learning from the real world.
The design goal for Zjit is incredibly ambitious. Build something fundamentally more maintainable and extensible, aiming for a lifespan of 20+ years as the core JIT within C Ruby.
20 years. Wow, long-term thinking.
Very long term. The idea is to lay down foundations so solid and well-structured that you can keep building on them and improving them for decades, rather than needing another major rewrite a few years down the line.
All right, gotta ask the critical question right away. Pronunciation. The speaker in the talk had a clear
Yes,
preference.
preferred pronunciation is Zjit.
It's
Zjit. Because, and I quote, it sounds more like Zjit.
fair enough. Zjit, it is. So, given that ambitious goal and the need to go beyond YJIT's architecture, what are the key design changes that make Zjit a truly next-generation JIT?
There are two fundamental shifts they're making. The first is a core architectural change. They're moving to a method-based JIT.
Okay, remind me, how did YJIT work again? It compiled YRV bytecode directly, right?
Yeah, straight from YRV.
And it was based on that lazy basic block versioning research aimed at getting quick, good performance initially.
Right. YJIT's architecture compiled the interpreter's bytecode pretty directly. It was based on that specific research strategy, lazy busy block versioning, from Maxim's PhD.
Okay.
And it was highly effective for its initial goals and getting results fast. But for JIT, they made a deliberate choice. It will not be based on lazy basic block versioning.
Interesting. So a different approach entirely.
It's adopting a much more traditional, established, method-based JIT compiler architecture.
Okay, why would you move away from something that was the foundation for YJIT's massive success? Is there a downside to that initial approach?
That's a great question, and it gets to the heart of the trade-off. While they have ideas for potentially extending lazy basic block versioning further, doing so is still very much a cutting-edge research project. It involves many unknowns and carries significant risk. For Zjit, which needs to be the foundation for 2 decades, the team wanted to make a much safer engineering bet. A method-based JIT is a traditional, well-understood way to build compilers. It has a known design, the challenges are well documented, it minimizes risk,
Right.
and there's a very high likelihood of long-term success because most highly successful JITs in other languages use exactly this approach.
So it's prioritizing a solid, proven engineering foundation over pushing the bleeding edge of compiler research for the core architecture. Stick with what's known to work reliably.
Exactly. The aim is a much more standard design, something you might see described in a classic compiler textbook.
Okay.
This architecture naturally leads to a more modular and extensible code base with components that can be swapped out, improved, or even rewritten over time without breaking the whole thing.
More maintainable, more adaptable.
Yes. And a huge potential benefit is that a more standard design should be much more accessible to newcomers and the wider Ruby community who might want to contribute.
Lower the barrier to entry for contributors. That's smart.
That's been a bit of a challenge with some of the deep specialized knowledge required for YJIT.
Makes sense.
Standard doesn't mean boring, though. You can build incredibly cool, innovative experiments on top of a stable foundation later.
Like maybe static basic block versioning you mentioned.
Perhaps, yeah.
Yeah.
Build it within this new, more standard structure.
Okay, major architectural shift to method-based. What's the second key design change in Zjit?
The second is that JIT will have its own dedicated intermediate representation, or IR.
An IR. And again, YJIT skipped that and compiled YRV bytecode directly.
Right. And while simple for initial development, YRE bytecode isn't really optimized for JIT compilation.
Why not?
It was designed for the interpreter loop. It uses bigger instructions to minimize dispatch overhead.
Okay.
Kind of like a CISC instruction set architecture. That's great for the interpreter, but not ideal if you're trying to perform complex optimizations in a compiler.
And an IR is, like the internal language the compiler speaks while it's thinking, its own internal code format.
Precisely. It's how the compiler represents the code internally, after it parses the bytecode, but before it generates machine code.
And why is that useful for a JIT?
The reason you want an IR in a JIT is that it lets you decompose complex original semantics into very small, simple, composable, primitive operations.
Break it down.
Exactly. This makes it much easier to perform various transformations and optimizations. Instructions in a good IR typically have very little internal control flow, making them more RISC-like.
Simpler pieces.
And much simpler for the compiler to analyze and manipulate. As the talk put it, referencing a documentary, risk is good. But in this case, the IR itself helps manage the risk of complex transformations by making them easier to reason about.
And Zjit is using an SSA-based IR. That sounds academic. Very compiler theory.
It does, but SSA static single assignment is the de facto standard in the compiler world for a very good reason.
Right.
It's used by virtually all major optimizing compilers today, from LLVM to GCC.
The big ones.
It was actually developed back in the 1980s at IBM and is taught as standard practice in universities now. It's proven to be incredibly flexible and robust for enabling advanced optimizations.
So again, standard, solid, proven foundations.
Exactly. It aligns with that goal for JIT.
Can you give us a quick glimpse of what that actually looks like compared to the YRV bytecode we might be more familiar with? The talk showed an example.
Yes, they showed the IR dump for a simple recursive factorial benchmark.
Okay.
Instead of just a flat sequence of YRV instructions, you see the code broken down into explicit control flow graph blocks.
Right, like branches visualized.
And the individual instructions are much more granular and explicit, things like fixed null for a less than or equal comparison.
Okay.
If false for conditional branching, fixed num sub for subtraction, send without block direct for a method call, much smaller pieces.
More primitive.
Exactly. And crucially, you see things like type information explicitly tracked for values,
Ah, the compiler knows more.
and mechanisms like patch points for de-optimization or guards to check assumptions and potentially exit back to the interpreter if needed.
So it's got escape hatches built in.
Right. It's a much lower level, more explicit representation that gives the compiler a lot more surface area and control to perform sophisticated optimizations.
Okay, so building on these more standard, robust foundations, a method-based architecture with a powerful SSA IR, what are some of the really exciting new features they plan to build into Zjit that weren't possible or were much harder with YJIT?
Two big ones were highlighted as potential game changers. First, fast JIT-to-JIT calls.
Ah, method calls in C Ruby are notoriously expensive, right?
Yep, a known bottleneck.
Because of managing two stacks, the VM's value stack and the C-frame pointer stack, and having to handle tons of edge cases.
So many corner cases.
Right.
YJIT did make them faster, significantly faster on microbenchmarks, 8 to 12x speedup.
That's already good.
It is, but the talk pointed out they're still way off the peak theoretical throughput.
Ah.
And the generated code size for calls is huge, which is bad for the CPU's instruction cache.
Right, cache misses hurt.
Meanwhile, languages like JavaScript have incredibly fast calls.
So how does Zjit plan to tackle this?
Exactly. YJIT's approach to calls often involves complex sequences of jump instructions and stack manipulation code to emulate the VM's call conventions.
Simulating the VM call?
Zjit's goal is to fundamentally change this by using the CPU's native call and return instructions,
Hardware instructions.
which are highly optimized by the hardware itself, and critically, using the standard C stack directly for calls between JIT-compiled methods.
So leverage the CPU's built-in function call mechanism instead of generating code to simulate it. That makes intuitive sense. Faster, less code.
It does. The trade-off is that you pay a higher penalty if you need to side exit from a JIT-compiled method call back into the interpreter.
Okay, so if something goes wrong or an assumption fails.
Right. But as the talk's analogy put it, think of the Shinkansen, the Japanese bullet train. It's incredibly fast, but it can't make sharp turns like a regular train. High-speed trains are still a great idea even with that limitation.
Good analogy. The speed gain outweighs the edge case cost.
The speed gains from native calls are expected to far outweigh the side exit penalty in most real code.
And they have early results on this. Does it work?
Yes, Kakashi Kokubun, who joined this JIT effort, recently got these fast JIT calls working. They tested it using a recursive Fibonacci benchmark. Now, this isn't how you'd actually compute Fibonacci efficiently.
Right, it's deliberately inefficient to test calls.
Exactly. It's specifically designed to stress method call performance because it's just function calling itself recursively over and over.
So how did Zjit perform on that compared to YJIT? What were the numbers?
Okay, so the interpreter is the baseline, 1x speed.
Right.
YJIT is about 10 times faster than the interpreter on this call-heavy benchmark.
10 times. Nice.
But Zjit, even in its very early state, is another 60% faster on top of YJIT speedup.
Whoa. So like 16x the interpreter.
Around that, yeah. And they see potential to eventually make it twice as fast as YJIT on this kind of workload, maybe 20x total.
That's incredibly encouraging progress for such a fundamental piece of performance infrastructure in a prototype.
Very encouraging, yeah.
Wow, that's a significant leap just on the call mechanism. Okay, second major planned feature. What else is big?
Serialization and persistence of compiled code.
Okay, explain what problem that solves. Why persist JIT code?
JIT compilation is always a balancing act. You want great code performance, but you also need fast warm-up times and low memory overhead.
Right, the trade-offs.
JITs operate in resource-constrained environments within the running application. Now think about a large organization like Shopify with thousands of servers.
Yeah.
Redeploying their application maybe several times a day, often 99.99% of the application code hasn't changed.
Right, tiny bug fixes usually.
But every time a server starts up, the JIT has to recompile all that code from scratch.
Wasted effort.
That is incredibly inefficient. You're redoing the same expensive work over and over and over.
So the idea is you compile it once and save the result, like caching the compiled code.
Exactly. The goal is to save and reuse the machine code that Zjit compiles by serializing it, saving its state, and persisting it, likely to disk or maybe a shared cache.
Okay.
The next time the application starts, or perhaps a different instance starts, it can load the precompiled code and hit the ground running, warming up much, much faster.
And the benefit goes beyond just faster startup. Is there more to it?
Yes, absolutely. This is key. If you know you can compile code once and then reuse that compiled version many, many times across multiple server starts or even across different servers,
Yeah.
you can afford to spend more time compiling initially.
Okay.
That means you can enable higher, more aggressive optimization levels that might be too expensive to run on every single server startup right now.
Because the cost is amortized.
Exactly. The cost of the high-level optimization is amortized over all the subsequent runs. You pay the price once, reap the benefits many times.
That sounds like a potentially huge win for production deployments, especially at scale.
Massive.
What are the challenges there? It sounds complicated to save compiled code that's hooked into a running process and then load it somewhere else.
It is definitely not trivial. You have to save not just the raw machine code instructions, but also all the associated metadata the compiler needs.
Like optimization info?
Information about optimization decisions, the optimization points, stuff like that. Crucially, compiled code contains pointers to things within the Ruby process.
Right, memory addresses.
Like inline caches, ICs, or even Ruby objects like strings or method structures. When you load that persisted code later, those pointers are no longer valid in the new process.
They point to garbage or unrelated data.
Right, so you need something like a mini linker that can fix up all those references correctly when the code is loaded into a new process address space. Relocation, essentially.
Wow, a mini linker just for JIT output. That sounds complex.
Well,
But it's something that's actually feasible. Have others done this?
yes, thankfully other JITs in the world have tackled and solved this problem. It's well understood conceptually, even if complex to implement.
Okay, so there's prior art.
Exactly. If they can make it work reliably in Zjit, it could genuinely be a game changer, especially for large companies with many servers and frequent deployments.
Okay, so that's the vision method-based, JIT, SSAIR, fast calls, persistence, big goals. Where does Zjit actually stand right now as of this talk, and what can we realistically expect for the upcoming Ruby 3.5 release?
As of the talk, the JIT was still very young, only about 2.5 months into development.
Just getting started, really.
But the progress is rapid. They've already implemented their custom SSAIR, the basic operations like comparisons and arithmetic, the control flow, the fast JIT-to-JIT calls we discussed, and even some basic optimizations like constant and type propagation and dead code elimination.
So it can run code, like simple stuff.
It can run simple micro benchmarks, and as we saw with Fibonacci, it's already faster than both the interpreter and YJIT on some of them.
That's promising.
However, they were very clear. This is very early innings. It is absolutely not usable for production or real-world workloads yet.
Got it. Experimental. What about getting it into C Ruby itself? Is that happening?
They've already opened a proposal to upstream Zjit into the main C Ruby repository.
Okay.
The goal is to make development much easier by being part of the core project, using the same build system, CI, etc.
That makes sense.
They've discussed it with the key Ruby core members who were reportedly very receptive.
Good sign.
And Mats himself expressed complete confidence in the Zjit team and is in favor of upstreaming it.
Wow, Mats is on board.
Yeah, the expectation was that this upstreaming would happen within a few weeks of the talk. So maybe it's already in by now or very soon.
And will users be able to play with it? Maybe flip a switch like with YJIT or -Zjit or something?
Yes, the plan is to have a command line option, Ruby Zjit, just like YJIT has Zjit.
Okay.
But again, that will be for experimentation only initially. They expect Zjit to become significantly more usable and stable sometime around the second half of 2025.
So still a ways off for general use.
Right now, they're focused on building the core foundations, but they're making very rapid progress.
Okay, so Zjit is coming. But what does that mean for YJIT in the immediate future, like in Ruby 3.5? Will YJIT be replaced or removed?
No, not yet. Definitely not for 3.5. YJIT will definitely still be available in Ruby 3.5.
Okay, good.
This is crucial to guarantee that the release ships with a fully working, stable JIT compiler that users already rely on.
Makes sense. Don't break things.
They won't remove YJIT until they are absolutely confident that Zjit is faster and just as stable on real workloads. However, to focus all their resources on Zjit,
Yeah.
YJIT is officially being put into maintenance mode. All the main development energy is now directed towards building Zjit.
So bug fixes for YJIT, but new features go into Zjit.
Pretty much, yeah.
So it might even be possible to have both JITs compiled into the same Ruby binary, like choose at runtime?
That's currently the belief that they can build both YJIT and Zjit into the same Ruby binary,
Interesting.
allowing you to choose which one to use with Ruby YD or Ruby DayZ.
Oh, that's great.
This is great because it means production users relying on YJIT don't need to change anything for Ruby 3.5.
No disruption.
But curious users and developers can start trying out Zjit in its beta state easily.
That sounds like a really smart transition plan. What's a performance target for Zjit by the time Ruby 3.5 is released, probably end of this year?
The hope is for Zjit to match YJIT's performance by the Ruby 3.5 release date later this year. Parity is the initial goal for the release.
Okay, match YJIT first.
From there, the expectation is that Zjit will start pulling ahead and beating YJIT on more and more benchmarks as 2025 progresses.
Right.
The ultimate goal is to significantly outperform YJIT, maybe even, as the speaker put it, wipe the floor with it eventually.
Ambitious.
But they are realistic that beating YJIT on the larger, more complex, realistic benchmarks will take time and sustained effort throughout 2025 and beyond.
So, exciting developments ahead, but a marathon, not a sprint for Zjit dominance.
Definitely a marathon.
What are the absolute immediate next steps for the Zjit team? What are they working on right now?
Well, the fast JIT calls are already working, which was a huge milestone thanks to Takashi Kokubu.
Huge win already.
The very next thing they're focusing on is adding the ability for Zjit compiled code to side exit correctly back into the interpreter.
Ah, the escape hatch we talked about.
Exactly. This should be done in the next few weeks, according to the talk.
And that enables what? Why is that so important?
That's the key to enabling much more extensive testing. Once side exits work, they can start running the full Ruby test suites against JIT, see what breaks.
Right, find the bugs.
More importantly, for performance, they can start running Zjit on all the benchmarks tracked by speed.yjit.org.
Ah, get it on the public dashboard.
Yes. The goal is to start publishing Zjit versus YJIT performance data on that site publicly sometime in the second half of 2025.
Make the race public.
They want to gamify the thing a little bit for the team by making the progress visible. Friendly competition.
Love it.
And from there, it's about the monumental task of gradually growing Zjit's feature set, compiling more and more of Ruby's complex operations correctly. Bignums, floats, method caching, blocks.
All the tricky stuff.
All the tricky stuff. And continuously measuring and optimizing the compiler itself, both how fast it compiles code and how fast the code it generates actually runs.
Constant tuning.
Constant tuning and implementation.
So what does this deep dive into the source material mean for you, the listener, and for the trajectory of Ruby as a language? The drive for performance in Ruby is clearly far from over.
Not at all.
The tremendous lessons learned from the real-world success of YJIT are directly informing and paving the way for a completely new JIT architecture in Zjit. This isn't just about squeezing out a few more percentage points. It's about prioritizing a robust, standard, and maintainable foundation
The 20-year vision.
that can support major innovations like persistent compiled code and lay the groundwork for peak performance for potentially the next 2 decades.
It really raises an important question for you to consider. If performance is truly becoming a matter of survival and long-term relevance for programming languages,
Which it seems to be.
in the face of relentless hardware and software optimization trends, how does this approach being taken with Zjit prioritizing a solid, standard engineering foundation with a multi-decade view compared to the evolution and performance strategies you've seen playing out in other programming languages you might be familiar with?
Yeah, like, is this conservative bet the right one? Or should they be taking more risks?
Is this the right path for Ruby's future? It's something to think about.
If you're interested in following this progress or diving deeper into the work, you can periodically check the Rails at Scale blog, where they often post updates.
Yeah, Shopify's engineering blog. And it's worth mentioning, if this kind of work excites you, that Shopify's Ruby and Rails infrastructure team is actively hiring for this.
Oh, cool.
They're looking for compiler experts, specifically for the Zjit project, C and Rust systems programmers, and world-class Ruby and Rails experts.
So if you want to work on this stuff,
If you're interested in joining this team and working on the future of Ruby performance, look for details on their hiring page. The talk even had a QR code, I think.
absolutely fascinating stuff. It's incredible to see this level of continued investment in making Ruby not just productive and enjoyable, but genuinely fast.
It really is. The future looks bright and potentially very fast.